Hello, everyone. Welcome back to CMPT 456 and 459. Today, we'll talk about data lakes. Many students told me that they are very interested in the latest development of data science, data management, data infrastructure in industry. Data lakes are popularly used in many companies, organizations, governments, and many large organizations. Therefore, I quickly grab some information related to data lakes. In this special section, it is open to both the CMPT 456 students and 459 students because both information retrieval and data mining, data analytics are used in data lakes. And we will try to give you a brief but still conceptually complete idea about what data lakes are and what are the major challenges and opportunities of using data lakes. And at the end of this talk, how to use open source tools to build a data lakes. What would be the architecture? Because data lakes are so new, the materials in this section will not be found in your textbooks. But I hope you still enjoy. Now, let's talk about data lakes. Data lake is a centralized repository storing all structured and unstructured data at any scale in an organization. In other words, in an enterprise or in an organization, we want to maintain one place where you can find all the data about the enterprise, about the organization. So you'd want to avoid the situation you have to ask different people in different departments, try to check every different corners in the department on the organization to find the data related or the data would be useful for your new project. Therefore, what about we just put everything into one place? That's the idea of data lake. Let's try to collect all the related information, all the related data into one repository. And later on, everyone can search that repository to find the information related to their information needs. So to that extent, data lake is the storage where data is stored as is. Different from data warehouses, in data lake, we do not first structure data. And for data lake, we do not do the structuring first. Indeed, data lake allows many different kinds of analytics. For example, from the dashboards and visualizations to big data processing to real-time analytics and machine learning to get the better decisions. So as you can see, because the diversity of tasks in data lakes and data lake organization would be very different from other data infrastructure in the enterprise, like data warehouses or transactional or operational data. So how can we compare a data warehouse and a data lake? As shown in this figure, a data warehouse is a place where data is processed and organized into a single schema before being put into the data warehouse. In other words, when we build a data warehouse, we need to first think about the enterprise strategy. What would be the major dimensions, major perspectives that our decision-making process should aim at? And then we organize the whole enterprise data set according to the strategies, according to the strategic directions, and put the data, organized data, into a multidimensional schema. However, for data lake, things would be completely different. We just store the raw and unstructured data into a data lake, stored as it is, And then later on, when the analytic task comes, we can start to try to manage the data, organize data ad hoc. And later on, we will see the important thing in a data lake is how we can find the data related to a task. If we get a closer comparison between data warehouses and data lake, we'll find they are different in several key aspects, including the data, the schema, the price and performance, and the data quality, users, analytics. In terms of data, data warehouses will focus on relational data from transactional systems, and it is a continuation of the operational databases in terms of data pipeline, and it aligns well with the business applications. Data lakes, on the other hand, is often consisting of non-relational and relational data from many different sources, such as the IoT devices, the websites, mobile applications, social medias, and corporate applications. So the data sets in data warehouses and data lakes are very different. In terms of schema, a data warehouse would have one unified and central schema that designed before the data warehouse is constructed, while data lakes will typically do not have a uniform or a general data schema crossing all the data sources. Instead, they will try to extract schemas for each data set and then just maintain a collection of those schemas. For data warehouses, we would like to try to achieve fastest query results using higher cost storage, while a data lake can be more distributed, can be more autonomous, where query results getting faster using low cost storage, because the queries may also be more diversified. In terms of data quality, data warehouses typically enforce stronger data quality control and would have highly curated data that serve as the central version of the truth. But data lakes, typically because of the much larger scale in terms of data sources and data usage, the data may not be curated and maybe just in terms of raw data, in the form of raw data, and thus the data quality may not be as high as data warehouses. In terms of users, data warehouses are targeted at business analytics and also the decision makers, while data lakes are often used by data scientists, data developers, and business analytics. So they are overlapping, but not exactly the same. In general, data lakes tend to support a much larger population in users and covers a larger scope. In terms of analytics conducted, a data warehouse typically support batch reporting, business intelligence, and visualization, while a data lake can support a much broader purposes like machine learning, predictive analytics, data discovering, and profiling. So as you can see, data lakes is the next step, continuing the data warehouse support to many analytics, and it supports a broader and more ad hoc analytics. Let's take a look at the enterprise data organization. Well, we know for a big organization, we may have structured data such as those relational data tables. We may have unstructured data such as those emails, documents, communication between customers and different staffs. And also we may have unstructured data with some schema. For example, we may have financial reports. The reports themselves are unstructured, but we have a schema to derive those text information. So, as we said, a data lake wants to collect all the data pieces into one place. Therefore, we need to load such data into a central data repository. For structured data, we typically do the parsing so that the data can get into the data lake. And for unstructured data, we do the extraction. We extract the information from the data. So this is similar to the crawling in the search engine. And because for structured data and unstructured data, we may not have the explicit schema. So one important task indeed is to do the schema inference. We try to, from the data, to learn, to derive the schema behind the unstructured data and the structured data. So we obtain the schema. Because we may also have some unstructured data with schema already. So such schema can also be imported directly into the schema storage. And that's the whole data lake. And once we have the data lake, we can construct and support all kinds of analytics based on the data lake data as well as the schema. Building a data lake is far from trivial. There are a lot of challenges. First, there are many data sets. Typically, in even a small organization, there could be hundreds of thousands or even more data sets. Also, a data lake has to support many sophisticated queries. For example, one may search a data lake using keywords. So this is something like a search engine. We use the keyword query to obtain the information. And another kind of queries which are very frequent in data lake is that I already have some data. I try to find the other datasets related to my data that can be joined to form a larger database so that to support my project and my analytics better. So this is the query of finding joinable datasets. Or I'm building a machine learning model. I'm trying to learn those features that are useful for my machine learning model. In other words, now I need to find features. Therefore, in order to satisfy all those different queries, one important thing is that we need to have good metadata. The metadata data can tell us where the related data is and what is the structure of those related data and how we can access the data. Therefore, a core task in building data lake is the metadata management. For example, let's look at one example here to understand the challenges of metadata management. Well, this is a table showing the homicide in Canada. And then when you look at these data set, you see, well, it is related to one research. But such as we want to understand the number and percentage of homicide victims by type of firearm used to commit the homicide. However, there are two attributes really hard to understand. What's the vector and what's the coordinate? Without the metadata, you cannot really understand what these two are, and thus the data may not be very useful for you. One challenge in building a data lake is data cleaning, because data is imported or stored in its raw form. Therefore, there could be all different kinds of errors and noises happened in data. To build a data lake, we need to conduct data cleaning. A lot of people realize that data cleaning is indeed the number one most cited task in data lake. And over 85% of the users consider data lake is the major or critical task to the success of the business. Let's look at one example here. You can see this is a table about the uh, yellow tax chip payment. As you can see, the payment fair amount here, range from a few bucks to over $10. Looks normal. However, there's some records having extremely large fair amount, and those extremely large fair amount is bothering because um, we don't know what's the real value. Those records do not look right. And typically, we don't take a taxi paid hundreds of thousands of dollars. So you can see data cleaning is very, very important in practice. A data lake contains data not only large, but also evolving. There are many duplicates as datasets, often being copied for new projects. And those duplicate datasets are also inserted and added into a data lake. Also, datasets are constantly being updated, having their schema changed, being derived into new ones, and removed or added back. So they are disappearing and reappearing. So, in order to handle data evolving, one idea is that we can do dataset versioning. Dataset versioning is to maintain different versions of datasets for storage so that the storage can be cost saving, can be collaborative, and it facilitated auditing, and also it is experimental reproducible. So data set versioning is one important task in data lakes. A data lake is like a zoo. It's a very diverse zoo. There are many, many different things going on in a data lake. For example, let's first look at the dataset formats on the dataset data.org, which is a data lake maintained by the US government. As you can see here, there are many, many different types of dataset here. We may have HTML here, we may have binary file here, XML here, and so on. So, indeed, the diversity of data lakes is caused by we try to harvest as many data sets as possible from multiple sources related to our business. You will face a similar challenge in this course project. Indeed, if you look at the data sets we provide you on the course project, you see they may be in different formats, they may be in different sources. So diversity is one thing you have to keep in mind for data lakes. A data lake is not only diverse in format, it also diverse in data providers, data publishers. For example, if we look at data.gov, the data lake by the US government, you can see that the data is contributed by many different departments. For example, Department of Energy, US Environmental Protection Agency, Earth Data Analysis Center, University State of Canada, California, and so on. So, because the data are from different organizations, from different sources, they may not follow the same standard. They may not follow the same format. They may not follow the same quality measure. And that makes a data lakes, dirty and needs a lot of effort to consolidate. And data formats, as we know in the open world, can be highly heterogeneous. Therefore, we need the injection and extraction task to bring structured data sets into a data lake, and we try to ingest already structured data sets and extract structured data from unstructured and semi-structured data sources. And also, because of diversity of the data sets, we need data integration, which is a task of finding joinable or unionable tables of those on-demand population, a schema with all the data from the lake that confirms to the schema. For example, in these hospitals, they use electronic health records. We need to enrich the electronic health records so that it can use data from different non-standard personal health record data sets for better predicting health risk. Here, we need to look at the possibility of joining or unifying different tables from different data sets and sources. This data integration is an important step in managing the diversity in data lakes. So I hope I give you some general idea about the motivation of data lakes, why we want a data lake, and then also some challenges and opportunities in the data lake. Therefore, we can have this figure. The common tasks in building a data lakes include several things: injection, extraction, for example, the type inference, and metadata management, which is sort of the core of a data lake, and cleaning, data integration, data discovery, and dataset versioning. So we have multiple data sources here. We have user here. And then first, we need to ingest and extract information from data sources. So this is a task of injection and extraction. Then we store the data in the repository. In order to maintain the history of data involvement, we need to do the dataset versioning here. And of course, when we get the data from the data sources, it is not just injection and extraction. We also try to clean the data so that the data can follow the high data quality standard. So this is the data cleaning part. And once we have the data repository, we try to populate the unifying data model, the metadata, and the data and metadata indexes so that we can support the discovery of the data and the integration of the data. So this building the schema here is a data integration. So let's look at some of the tasks in a little bit detail. By the way, due to the time here, I won't go very, very deep into each task, but I tell you a little bit of what it is doing so that you can find the corresponding tools for the specific task. Injection. So we have both structured data and unstructured data. We do through the parsing, we can import the structured data into a data lake. For unstructured data, we need a little bit more work to do the extraction. For example, we may use the natural language processing tools to extract the data into data lake. So those are the topics we already covered in the web crawling, in the information retrieval tasks. Extraction. Now, let's look at extraction a little bit. We can extract data from unstructured data sources in different ways. For example, we may extract data from web tables, or we may use the log files in websites, in data sources to extract the information from unstructured data. Indeed, there are lots of tables available on the web. The web tables would be very useful for building a data lake. Just let's have some basic idea about how big the public access web tables would be. As you can see here, a common core of the web tables so far from 2011 to now have around 2.6 billion web pages in raw HTML. Those pages can be found from two major archives. One is the Web Data Common Web Table, WDC, which contains both relational tables, pivot tables, and entities. Another archive is the JSON Web Table corpus, which contains both relational tables and pivot tables. For the WDC web table, WDC refers to these web data commons. The URL is this one. You can visit the archive here. In the core of 2015, it has 233 million web tables, which consists of around 90 million relational tables, 140 million entities, and 3 million matrices, which are also called pivot tables. The corpus also provides metadata training. The features include, for example, the orientation of the records, whether it's a row table or it's a column table, and the title of the HTML page, which can help us to understand the source, the content of the table. And also, once you have a table, the text surrounding the extracted table may be useful to understand the content, the semantic of the table. Therefore, the archive also provides the text surrounding the extracted table. The JSON web table corpus contains around 125 million tables, where the data table is identified and extracted by a classifier, which is learned from a training data set. So it collects not only the horizontal table, but also vertical and matrix tables. The classifiers uses 127 features for each HTML tag table, and use some features like a max and average cell count per row and column, and so on. And the training dataset has 2,000 data tables manually curated. So the training dataset is of high quality due to the manual curation. And the correlation-based feature selection is used to perform this feature selection, which produces about 30 useful features. This is the architecture of a journal metadata management. As we said, the metadata is one of the core function in a data lake. So as the basics, we have the data sources, and we have the metadata sources and the services. We use crawling, injection, schema inference to produce the metadata. The metadata will be integrated into the metadata model and managed by the metadata management system. We'll give some examples in a few minutes. And then on top of this metadata management system, we will have different metadata services, such as discovery, integration, versioning, and so on. There are several major ideas behind metadata management in data lakes. First, we can enrich data and metadata with semantic information so that we can support the template-based query on metadata. In other words, for metadata, we cannot allow arbitrary types of query which may be too challenging. Instead, we try to understand what would be the typical queries on metadata. We support such typical queries using meta-based queries so that a user can just tune the parameters of a template to search for the metadata. Another idea is that we can extract those deeply embedded metadata, such as the metadata within, for example, related to an image, related to text, related to table, and also the contextual metadata. For example, by understanding the surrounding information related to one picture or one table, we can understand the context of the data entry. So by extracting such embedded data and contextual metadata, we can support the topic-based discovery because the topics are typically well explained by the metadata and the context. And also, we can integrate metadata about data, users, and queries, and use visualization to help the support and the analysis of metadata. So let's take one example, goods, which is the data lake internal to Google. In Google, the internal data lake has tens of billions of data sets. Those data sets, some are very large, like in the gigabyte and terabytes scale. For each data set, Google produces an entry in the metadata record. The entry contains the basic metadata, the provenance where the data is from, how it is derived, the schema, and also a summary of the content. So it looks like this. We have the data set path. We know the size. We know the provenance. So which process derives this data set. And also we have the schema link here. So we are trying to provide such metadata for you for the data sets to be used in this course project. So you can find the metadata information description in the resource webpage of this course. So the metadata can come from many different sources. In order to derive such a metadata base, we can look at the content samples so that we can summarize the content. We can look at the logs from where we can understand the provenance and also the size, the source code repositories, which can also provide us some hints about how the data is produced. Cloud sourcing can help us to annotate the data. We may also have knowledge bases to help us understand the relationship among different data sets. Now, at the end of this section, let's look at how we can build a data lake. What would be the architecture of a data lake? So this figure shows a conceptual architecture of a data lake. At the lower level, we have data warehouses, we have managed document repositories, we have file shares, we have databases, we have cloud or external data sources. In other words, we have all kinds of data sources available to this organization. We just collect every piece, every bit that can be useful for an organization. Those data sources are connected to our enterprise data lake through connectors. Those connectors will help us to do the injection, extraction, all those things. And then once the data get into the data lake, we can do the big data analytics and reporting. And also the reporting results should go back to the data lake, which can be used by a search engine to find the related information. So here we have the big data models and dictionaries, and we also have business rules and dictionaries here so that we can take the input from business user interface. And we maintain the API to support, for example, user events, web browsers, mobile, web, and also apps. That's the global conceptual structure architecture of a data lake. Well, there are many different ways to build a data lake, and you may be interested in how to use open source tools and platforms to build a data lake. Here we are. From the user, we can use Jupyter to learn to use a data lake, and the data can be input as the Kafka data into the data lake. The data can be stored in the Hadoop file system, the HDFS, and then use the Hive to interact with the data, with users. And also, we may use the Elasticsearch, which is open source, search engine to interact with search. And we have used the Kubernetes to build everything onto a cloud platform. And we can use the open Whisky data crawler to crawl the metadata store. So you can see we can use a few these open source packages to essentially get the basic structure, basic architecture of data lake. And of course, in order to support the data analytics, we can use TensorFlow or any MXNet, those things to build machine learning models. We may also use Spark to compute big data analytics. And also we may use Airflow here for any ad hoc and ETL clusters here. So, in conclusion, in this short section, we talk about the motivations and the concepts of data lakes. And data lakes are new infrastructure in enterprises and organizations. It provides a lot of new opportunities and convenience, but at the same time, it is also facing a series of technical challenges and tasks. And we talk about some data lake architectures, and that would help you as the starting point so that you can continue your exploration if you are interested. Thank you, and I hope this section is interesting and helpful for you. See you next time. Bye-bye.